Okay, circulation. We need to talk about circulation predominantly at this point from localized regulation. So tissues have the ability to automatically adjust their own blood flow to match their metabolic demand for supply of oxygen and nutrients and removal of waste. That process, that ability to automatically adjust a tissue's own blood flow is called autoregulation. Um, you can see this through local changes, local factors. So, um, and they're gonna act at the capillary bed. Remember, we're dealing with pressure at the capillary bed. So temperature, potassium and hydrogen ion concentrations, lactic acid, nitric oxide, oxygen concentrations, any of those things are going to play a factor. But when we talk about regulatory responses, we need to look at a very important set of differences between the pulmonary side and the systemic side of this circulation. So when we talk about systemic blood vessel walls and we talk about hypoxia or low blood oxygen, what we're going to see in response to hypoxia or even acidosis, a high positive ion concentration, we're going to see those systemic vessel walls dilate to increase the blood flow. So when we have tissues that aren't receiving enough oxygen, that they're hypoxic, the response on the systemic side is to dilate those blood vessels. And we're going to do that because we want to increase the blood flow and hopefully increase the oxygen and get those tissues the oxygen that they need. Now that's very, very different than on the pulmonary side. So on the pulmonary side, we're in the lungs, right? And so when we have hypoxic or an acidotic situation in a specific area of the lung, the stimulus response is to constrict those vessels. What we're doing when we do that is we're constricting the vessels in the area where we're not getting good gas or hydrogen ion exchange. So we're diverting blood flow to areas with better ventilation, with better ability to deal with the acidic situation, the acidosis. So we have two very different response in the autoregulatory system when we talk about systemic hypoxia versus pulmonary hypoxia. And if that's not really clear, I want you to jump back into your textbook and read about that a little bit. We can talk about it in class, or you can send me a message if we're talking about the online class. I want you to really grasp the difference in that autoregulatory response between systemic and pulmonary hypoxia. So let's talk about how we clinically evaluate circulation. Remember, we talked about not being able really to easily measure blood flow, right? So we were gonna measure pressure instead. But before we jump into that, I want us to talk about pulse as a pressure wave. So remember that pulse happens as the result of a pressure wave. So we have an expansion and a recoil of those elastic arteries, and those happen after each systole of the left ventricle, right? So the systole was contraction, right? So when that ventricle contracts, I'm going to have an expansion of that arterial vessel, and then as ventricular diastole occurs and that chamber relaxes, I'm going to see that vessel start to recoil back to its normal diameter. Pulse rate is typically between 70 and 80 beats per minute in most individuals. Some higher, some lower, it's that whole individual results will vary sort of situation. But how we actually look at measuring blood pressure, and you do have to know how to spell this word, we measure blood pressure with a device called a sphygmomanometer. Everybody say it, sphygmomanometer. It's spelled just like it sounds. And what we're looking at in measuring blood pressure is we're measuring the difference in pressure at diastole and systole, or rather, I think it's written on the slide, systole versus diastole. So pulse pressure is that difference. It's that difference between systolic pressure and diastolic pressure. Now, before we tackle that, I want you to grab some keywords for me. One of those words is tachycardia. Tachy means rapid. Cardia is heart rate. So in tachycardia, we have a heart rate greater than 80 beats per minute. The opposite of tachycardia is bradycardia, B-R-A-D-Y, bradycardia. Bradycardia is defined as less than 60 beats per minute. When we talk about systolic blood pressure, we're talking about ventricular contraction. When we're talking about diastolic blood pressure, we're talking about ventricular relaxation. And what that does is it provides some information to us. The reason the diastolic number is important is because it gives us some information about the vascular resistance. How much resistance do we have? When we talk about ratios, our ratio should be 3 to 2 to 1. So our systolic blood pressure should be our 3, our diastolic pressure is our 2, and our pulse pressure is 1. But let's actually take a look at something here. Let's look at this. So we're actually, I believe we're going to do this in lab, but you've got blood pressure at about 120 over 70. You're going to put on that cuff, the cuff being part of the sphygmomanometer. You're going to raise the pressure in the cuff above 120 millimeters of mercury. You're going to keep going up that high, and what you're doing is you're constricting that blood vessel. So as you put that external pressure on around the arm with the cuff, you're constricting down that brachial artery inside the arm, and then the artery closes. So what you're going to do is you're going to slowly release the pressure in the cuff so that what can happen is the blood can start to flow. And when it does that, you're going to start to hear the sounds with the stethoscope. That's the first number you're going to take. Okay? That's your systolic number. And you're going to continue to slowly release the pressure on that cuff until you no longer hear the sounds, until that vessel is fully opened up again and you can no longer hear the sounds. And that last sound, that point where you last hear a sound, that's the diastolic blood pressure. So remember, we're going to measure the blood pressure in the arteries that's being generated by the left ventricle during systole, and the pressure remaining in the arteries when the ventricle is in diastole. Let's take a break here. We'll come back and talk about hypertension.